Hello and welcome back. Today we are going to start talking about Chapter 8. Now, Chapter 8 introduces the concepts of potential energy and also conservation of energy. Now, that said, this is going to be the first of two lectures for this chapter, and I'd like to start by reminding you about some results that we got when we were talking about Chapter 7, specifically the work energy theorem. Now, we had defined work through differential work, which looked like this. Now, let's not remember, this is the force that we are applying to something, and this is the path that that thing is taking. Now, the force might not be along the path, as we saw last chapter. It's possible to have orientations of forces and paths that give you no work at all. We also talked about how when you actually do the work, we'll say go ahead and just integrate both sides to make it look nice here. That as a consequence, you get a change in kinetic energy. We define kinetic energy, through a derivation, and it looks something like this. Now, let me just be consistent here with limits of integration. So remember, work is energy, and all of this stuff sort of was adopted and overlaid from Aristotle. Okay, so the idea here is that this energy is coming from somewhere. And as we had talked about last chapter, that somewhere appears to be within forces somehow. Okay. Now, so the thought process that I'd like to take here, at least initially, is that if this work is coming from somewhere, we can define its source. Now, we're going to call that source something called potential energy. So, if you want something to think about, you can think about the fact that kinetic energy deals with motion, and potential energy deals with forces. And forces are the things that can potentially cause a change in motion. Now, so we're going to use the letter U for potential energy. And if you do work and you cause a change in kinetic energy, that work is also going to cause an accompanying change in potential energy. Now, the negative sign is here to tell us that whatever change this experiences, this is going to experience the opposite. So you can think of them sort of like containers. We'll call this the potential energy container right here. Maybe this is the kinetic energy container right here. So potential energy. So the reserve is we'll call delta U. And this is kinetic energy. And the reserve here we're going to call delta K. And basically what's happening here is that work is the mechanism. Okay, it's the tool that we use to take energy out of the potential into kinetic. And in a situation like that, you'd say you were doing positive work. It's also the mechanism that we use to take energy out of motion and put it back into this reserve that has something to do with force. And in a situation like that, you'd be doing negative work. Okay, so what I'd like to do today, at least initially, is to talk about how we find potential energy. Now, with kinetic energy, it's pretty easy. Right now, we're dealing with, as I mentioned last time, something called translation. And with translation, you're going from point A to point B in space. Okay. So this is kinetic energy that deals with that type of motion. Later on, we're going to talk about rotational motion, which is rotating about a fixed point in space or some point that might be moving. And then you also have kinetic energy as well. It's rotational kinetic energy. But nonetheless, in both cases, the form of your kinetic energy looks the same. Okay. So it doesn't matter how fast your object is moving or what caused it to experience a change in motion, K is always going to have a form that looks like this. Okay. On the other hand, potential energy arises from force. And as we discovered, say, back in chapters, 4 and 5, and potentially 6, forces have all sorts of different shapes. Okay, they have all sorts of. They look different. Okay, and as a consequence, you're going to have a different potential energy for each force that you come across. Now, the nice thing here, though, is that you can come up with the form of your potential energy for a specific force, write that down, and just refer back to it. So once you find the potential energy for something, typically you don't have to find it again, which is pretty nice. Okay, so that said, the process for finding it, in part, depends upon the fact that both of these, both kinetic energy and potential energy, when related to work, deal with changes. Okay, so let me just give you an example of what I'm talking about. Let's pretend that you started off with an initial kinetic energy of 1,000 joules, and you ended up with a final kinetic energy of, I don't know, 800 joules. If I asked you to find the change in kinetic energy in this situation, you would just subtract. It would be final minus initial, okay, which would be 800 joules, minus 1,000 joules, which is 200 joules. Okay, but what if instead your initial kinetic energy was 200 joules and your final kinetic energy was 0? What would the change be then? Well, again, 0 minus 200, sorry, this is negative, 200 joules is minus 200 joules. Okay, so what I'm trying to point out here is the following. It doesn't matter what your final kinetic energy or initial kinetic energy is when you're dealing with work energy theorem in a situation like this. What we care about is the change. Okay, the change is what's being driven by the work. Okay, now ultimately, at the end of the day, when you're actually using things like kinetic energy to solve for velocity, your initial and your final definitely matters. But with respect to potential energy, if you think of delta U as being U minus U naught, okay, then here it's this change in potential energy that powers, we'll say through work, an accompanying change in kinetic energy. Okay, so the important thing here is that you may not, for example, know exactly what your final potential energy is, but you can set things up such that the change is what we get, and we're going to see that here in an example here in a second. Okay, so that said, what I'd like to do is to let you guys focus on this for a moment. Keep this in your heads, and let's do an example. This is gravity, so let's talk about gravity. Gravity is an easy one. So here we have a mass. We'll say I'm going to be very abstract here. I'm not going to put numbers in. Okay, so it has a mass of m. Okay, we will start our thing off here with an initial position in y of 0. And you have this table or cliff or building. It doesn't matter what it is, just as long as you're above the ground. And down over here, this is our final position y. Okay. Now, what I'd like to do is to let this mass sort of fall off this table or whatever it is and fall towards the ground and hit the ground. And what I'd like to find here is the potential energy that this mass has, specifically up here. I'm trying to find the equational form for potential energy when you're dealing with gravity. Now, we know as the mass falls, it's falling because there is a force being exerted on it. It's a gravitational force, which is causing this thing to fall downwards, right? To the tune of m times g y hat. All right. Now, we also know if this thing starts from rest, which is what we're going to assume, that as it falls downwards, it's going to go faster and faster and faster. So in a situation like that, you're going to have a change in kinetic energy that's going to be positive because in this particular situation, like I said, your mass starts from rest, and when it gets to the bottom, it's going to be traveling, at some speed v. Okay. So what I'd like to do is to find the amount of work that's done by gravity taking this mass from this location right here to this location right here. And then we're going to use that to find what the form of potential energy looks like for gravity. Okay. Now I want to be very clear. This is gravity close to the ground. All right. As you get further and further and further away from the Earth, the form of gravity goes from being constant to depending upon 1 over r squared, which is something we're going to be talking about towards the end of the semester. Okay. So in this particular case, though, we're just dealing with constant gravity. Now, incidentally, when we do talk about the full-fledged version of Newtonian gravity, we will find its potential energy using the same process. Okay. Now, that said, let's talk about the work. So again, we're dealing with a constant force, which is really convenient for us because we know in situations where you have constant forces, your work is just F dot delta R. Now, this is the direction of F. This also happens to be the direction of delta R. Okay. Now, in this case, delta R is minus delta Y, Y hat. Okay. So when you do F dot delta R, since they're parallel to each other, the cosine that sits there is going to be 1, and we're just going to be dealing with the magnitudes of these things, which will be F sub G times delta R, or delta Y rather. Okay. Now, so this is what the work looks like, and I'm not going to plug why not and why in here yet. Let me just go ahead and plug in what this looks like, though. All right, so this is the work. Now, so work we know is going to cause a change in kinetic energy, but it also causes an accompanying change in potential energy. And again, remember the negative sign is there to remind us that it's coming out of here and going into here, or it's coming out of here and it's going into here. If there's a positive change in kinetic energy, you should see a negative change in potential energy. So our change in potential energy here, or at least the negative one, looks like m times g times delta y. Okay. Now let's just go ahead and plug in u minus u naught for that, and y minus y naught. Okay. Now, so that said, if I multiply this negative sign through, I get minus u plus u naught on the left-hand side. On the right-hand side, if I put in the fact that my initial starting position we're going to call 0, okay, I get mgy. Okay. Now, y, remember, is a negative thing. It's negative because we're going down. All right. So what I would like to do in order to preserve the fact that these are magnitudes here is to put in mg, the absolute value of y. Remember, this has to be positive, so we're making it positive. Now, on the left-hand side, if you take a look at this, will you agree with me that as I sit above the ground here, when this mass is released, that the force of gravity is capable of making it move faster and faster and faster? Well, yeah, of course, that's what happens. So if you think of that from a standpoint of potential energy, that is, there is energy present to be transferred to motion, then that means that the potential energy up here at the very top is not 0. At the very bottom, though, when this thing hits the ground, it's not able to move past the ground. Okay? So there is no more potential for motion down here. And if there's no potential for motion beyond this point, the potential energy at the bottom we say is zero. Now, that's okay. As I pointed out earlier, what matters is the difference, like this, for example. Okay? So we are free to set this zero as long as we deal with delta U's, which is what we're doing right here. So my final potential energy, since I can't move past the ground, is zero, which means that my initial potential energy is m times g times the absolute value of y. Now, what's the absolute value of y? Well, it's how high above the ground I am. It's how high above the point of release I am. Okay? So sometimes we call this h, and you see your potential energy here written as mgh, or mg times the absolute value of delta y. This is the potential energy for gravity. Okay? And as a consequence, you can just box this, start, and put it in your notes, because it's something that we can always refer back to. That's the convenience of it. Now, we're going to do an example of this here in a little bit. But what I'd like to do is to do another example dealing with a spring. Okay? Now, in this particular situation, we have a spring that sits at the equilibrium position. So my initial position here, let's get rid of that. My initial position here is zero. Now, the spring is going to move to the right because our mass has an initial velocity that's not zero. But as it moves this way, this is the direction of dr. Because it's moving past the equilibrium point, the spring force is trying to slow it down. Now, we know in a situation like this that between this point right here and this point right here, this mass is going to slow down. So what that means is that we expect negative work, okay, because it's slowing down. So dW is equal to F dot dr. Now, dr in this case is equal to dx times x hat, because it's in the positive direction. F in this case is the spring force, which looks like, because it's going to the left, minus k times x hat. So when we look at the differential work and we do F dot dr, here F is minus kx x hat, and dr is dx x hat. So the dot product between these things is going to give us a minus k x dx, which makes sense. Okay, the dot product between them gives you a negative number because they're anti-parallel to each other. So the work that's being done by the spring between the points 0 and x, okay, x naught and x, is going to be minus kx dx. Now again, the negative and the k are constants. You can bring them out. And we're integrating this right here. And we know the integration rule for this. You're going to get minus k times 1/2 x squared evaluated from 0 to x. And when you plug in your limits of integration, you get minus 1/2 k times x squared, which is going to be a negative number. No matter what you put in here, it's going to be negative because of the fact that you're squaring the x. So in this particular situation, this is the work that's being done. But we know work causes a minus change in potential energy. Now, at this point right here, we're at x is equal to 0. The force from the spring right here looks like minus kx x hat. If x is equal to 0, the force is 0. No force, no potential energy. You can't move something if there's no force there, right? Or at least you can't cause the motion to change. So what that means is that if this is our initial position, our potential energy at that location is 0. So minus u is equal to minus 1/2 kx squared. Aha. The potential energy in the spring is 1/2 kx squared. Again, something that you can box and put a big old star next to, because that's what the potential energy for a spring looks like. Now, this is pretty sweet if you think about it, because we just found the potential energy due to gravity, which typically, like I said, this is actually written as U is equal to mg times delta y. They get rid of the u naught, okay? And it's just understood that, this is the starting position and you're above the ground. So check this out. If you go back and you think about work, and you think about how it causes a change in kinetic energy, and as a consequence, you see an accompanying change in potential energy. What I'd like to do is to focus on these two things right here. So change in, we know, means final minus initial. So on the left-hand side of that, you would have K minus K naught. Okay. This would be your kinetic energy at the end of the day. This would be your kinetic energy at the start of the problem. On the right-hand side over here, we have minus U naught. This is your potential energy at the beginning of the problem, and this would be your potential energy at the end. Now, what I'd like to do is to take this minus K naught and move it to the right-hand side, and then take this U right here and move it to the left-hand side. Now, when I do, because you have this negative sign here, it's going to become positive. Just like this negative is going to go through and make this positive, and when I move this over to this side, it becomes positive as well. So what I'm going to have on the left-hand side is going to be K plus U. And on the right-hand side, I'm going to have K naught plus U naught. Now, so if I look at all of the things that are moving in my problem and add them up, I'll get a total kinetic energy. If I look at all of the things that could potentially cause motion, the forces at the beginning of a problem, we'll say, then I add them up, I'll have all my potential energy. And here's the deal. All of the kinetic energy that's present at the beginning of a problem, plus all of the potential energy that's present at the beginning problem, if you add those two things together, you get all of the kinetic energy at the end of the problem plus all of the potential energy at the end of the problem. So what you start off with from an energy standpoint and what you end up with from an energy standpoint, where they're the same. Now that actually sounds pretty familiar to me, because if I remember correctly, there was this thing that you learned, say, back in K through 12 or high school or whatever it is. That it goes something like this. Energy is neither created or destroyed, it's only transformed. If it's not created or destroyed, that means the amount of energy that you have present doesn't change. Wow. We call that conservation of energy. And guess what this is? This is conservation of energy. Okay. Now here's what they meant by that whole creation and destruction cycle. So here, we're not creating or destroying energy. We are transforming it from potential to kinetic, or from kinetic to potential. That's what they mean when they say it's transformed. Now we're going to see more extreme examples of this in the second semester, because it turns out that energy in motion and energy in the things that can cause changes in motion, well, that's pretty consistent across the board. Okay? When we talk about, for example, temperature and heat, we'll be talking about energy. And it turns out that heat energy, well, that's just related to motion or the potential for causing changes in motion. When we talk about electrical stuff, for example, we know that you can power devices. If you power a device, that means that you're putting energy in over time. That's what power is. That energy ultimately comes from things that are moving, specifically electrons typically, or the potential for motion, which comes from, we'll say, the electric field or the magnetic field, which can cause things to move through forces, the electrical force and the magnetic force. So, this is pretty integral to the entirety of physics. There is one small change that's made later on, though. If you were to make a jump from classical physics, which is what we're doing now and what we'll be doing basically in the second semester, to modern physics, where we talk about quantum mechanics and relativity, there is one additional source of energy, which we're not going to be dealing with, and that is energy and mass. And that's it. Okay? So, this is a big deal. Now, I want to be very clear, though. Not all forces are conservative forces. Not all forces maintain conservation of energy. And we're going to be seeing examples of that shortly. That said, though, let's do some examples. So, well, I'll tell you what, before I do this, let me just formally define this. We call E energy. It's K plus U. So your initial energy would be K naught plus U naught. And the idea is that the energy that you start off with is the same thing as the energy that you end up with. So what you start off with is what you end up with. So if you were to move this to the left-hand side, what that means is that the change, why I'm writing K, the change in energy overall is equal to zero. In a situation like this, energy is conserved. Now, there are situations in which it may not be equal to zero. For example, maybe you have an experiment running and there's energy from the outside that's making its way into your experiment. Inside your experiment, you may think of energy being conserved. But if you're dumping energy in from the outside, that means that you have a source coming in. So if the system ends up being able to use that energy, that means that the change in isn't going to be zero. Okay. You also could have examples where energy is being lost to the outside. Okay. For example, through friction, and we'll be seeing an example of that later on. We'll be talking also about how you can determine as to whether a force conserves energy or if it doesn't. Okay, so that said, let's move on to this. A rock initially at rest is dropped from the top of a building that is 20 meters high. How fast is it traveling when it hits the ground? Now, this is a simple 1D kinematics problem dealing with free fall. It's dealing with free fall. You know what that means? If it's dealing with free fall, that means we're dealing with gravitational potential energy. That's pretty nice. Okay, so we'll have our rock start off here. Okay, it's starting from rest. That means that our initial velocity, which I'm just going to call v naught, is zero. Okay, when it gets down to the bottom, its velocity is definitely not going to be zero. Now, we know that it can't act past the bottom. Okay, so when it gets down here, we know that our potential energy down here is going to be zero. But we know because our rock is moving, our kinetic energy is definitely not going to be zero. Just like up over here, we're starting off from rest, which means that our initial kinetic energy is definitely equal to zero. But we have the potential to move, which means our initial potential energy is not equal to zero. Oh. Well, now this is interesting. Okay. Now I'm going to call. I actually personally prefer to write this as MGH. This is just a preference. You can stick with delta Y. And I'm going to call the height of this building right here. The starting point basically is 20 meters. Okay. So here's what I know. My energy at the top, okay, is K naught plus U naught. But K naught is 0. My energy at the bottom is K plus U. But U at the bottom is 0. Now, what's my initial potential energy? Well, it's my mass times G times how high above the ending point I am. What's my final kinetic energy? Well, K looks like 1/2 mv squared. And here's the deal. They're equal. So if they're equal, what that means is that E is equal to E naught, or 1/2 mv squared is equal to mgh. The masses cancel, and V is the square root of 2gh. Now, this should not be a surprise at all. In fact, you may actually remember this result from working problems like this. Likewise, you'll notice that there's no mass because this is gravity. Gravity causes all things to fall at the same rate. Okay? So, here, the square root of 2 times 9.8 meters per second squared times 20.0 meters. And when you do the math here, grab my calculator. Where's my calculator? What? My daughter stole it. Ugh. Short people. Okay, let me do this on my phone then. You little thief. I can't believe that. She's 3. She's like a magpie. So if I do this, I get 19.798 799 meters per second. You keep it, to 3 sig figs. This is 19.8 meters per second. Now, I want to be very clear, though. This is how fast. This has no directional information in it at all. And that's one of the issues that you have when you deal with energy that I mentioned, I believe, last time. And that's when you work an energy problem, you're dealing with numbers. You're not dealing with, vectors. I mean, sure you are when you calculate things like work and what have you. But at the end of the day, you end up with a scalar. So at this point, you would have to determine direction. Okay. But very easy. Here's another example. A spring sits on a table that has a mass of 2.5 kilograms and has a mass of 2.5 kilograms attached to one end, while the other is attached to a wall. The mass is displaced 15 centimeters from the spring's equilibrium and released from rest. If the spring constant is 330 newtons per meter, how fast is the mass traveling when it crosses the equilibrium position, and how far does the spring compress when the mass crosses the equilibrium and comes to rest? Okay, so that said, let's draw us a picture. So here's our wall. Here's our table, like that. Let's draw our spring. Remember, our spring has been stretched from equilibrium. So here it is. It's been stretched. Let me draw my mass here, right here. Okay. So what do we know in our picture? We have a mass of 2.5 kilograms. I'm going to call this position right here equilibrium. This is x is equal to 0. This over here, at least for part A, and let me just make this picture in reference to part A. So this is 15 centimeters from the equilibrium position. So this right here, my initial position here would be 0.15 meters because it's 15 centimeters. We also have a spring constant here of 330 newtons per meter. Now, we know it's being released from rest, so our initial velocity is 0. So we're given for part A, initial velocity is 0, spring constant of 330 newtons per meter, mass of 2.5 kilograms, and initial starting position of 15 centimeters or 0.15 meters, and our position that we're trying to find the speed for here is at 0 at the equilibrium position. All right. So for this part, we're trying to find v. All right. Now, so let's talk about energy. So at the start of the problem, with this thing that's being stretched, will you agree with me that, as stated, it's not moving? So if I was going to look at my kinetic energy at the beginning, it's going to be 0 because it's not moving. However, we know this thing has been displaced from equilibrium. The spring is trying to pull it back to equilibrium position. So if I were to let this thing go, it's going to move. So there's definitely a potential for motion here. What's the potential for motion? Well, I mean, if you go back and you look here, there's the potential energy for spring. One half k x naught squared. Now, when it hits the equilibrium position, at equilibrium, it's moving. But, as I pointed out earlier when I did the derivation for you, at equilibrium, the potential for motion is 0. So if we were to look at the initial energy here, which would be k naught plus u naught, k naught is 0, meaning that we're starting off with this much energy present. When it crosses the equilibrium position, it has k plus u, but there's no potential present at equilibrium position because the force is 0. 1 half mv squared. And these are equal to each other because of conservation of energy. So if they're equal to each other, that means 1 half kx naught squared is equal to 1 half mv squared. The halves cancel. V is going to be the square root of kx naught squared over m. (330 newtons per meter times 0.15 meters squared divided by 2.50 kilograms. So if I put this in my calculator, I get, let's see here, 330 times 0.15 squared divided by 2.5. About 1.72 meters per second. Now, keeping in sig figs if you want, I see 2 here, I see 3 here, I see 2 here. So this would be about 1.7 meters per second. So there's part A. Now you'll notice we didn't have to talk about the physics of what's going on for the spring to get from here to here, or for this mass rather to get from here to here. All we did is look at what the energy was here and what the energy was here. And that's one of the powers of the energy approach. Okay, it's incredibly useful. Now let's do part B. For part B, oops. We have a similar problem. What I'm going to do is sort of snag this, yank it. Actually, one will also get the givens as well. Whoops. Copy and then paste. I'm going to yank it and put it there. Let me clean it up a little bit. You can go away. Now what's happened here is, and we already know what a lot of this information is. We're going to restate what we need. What's happening here is this thing is now at the equilibrium position. Okay. So here it is. It's moving though. It's moving to the left. So it has an initial velocity because it's hit this equilibrium position from being released on the right. So what's going to happen is this mass's inertia is going to carry it past the equilibrium position as the spring works this way to try to slow it down. So the spring is going to work this way trying to slow it down. And eventually it's going to release it. It's going to reach a compressed position. Whoops. A compressed position somewhere over here, which we're going to call X. So here, in this particular situation, our initial position is the equilibrium position. So, and here, we're trying to find this. Because remember, we want to find out how far the spring compresses when it actually crosses and comes to rest. Oh, it's at rest, which means that we know our velocity at this point right here is going to be 0. And we actually know what our velocity is here initially. So, if I sort of adjust the givens over here the following way, our initial velocity, or at least the magnitude of our initial velocity, is about 1.72 meters per second. Our initial position now is at 0, so equilibrium, and we're trying to find this right here. But we also know that V at this compressed position, because it's brought it to rest, is 0. Okay, so this right here really is what we're trying to find. Let me delete that. I'm going to put that in a find. Okay, and again, initially, if I look at my kinetic energy, it's 1/2 mv naught squared because it's moving. It has energy in motion. But we know from our conversation when we're doing part A, and we actually derive the form of U, that our potential energy at the equilibrium position is 0. Now what's carrying it past the equilibrium position is the fact that this mass is moving. So it has inertia. And that inertia, we know, offers resistance to changes in motion. That's what the definition of inertia is. So it's going to cross it and compress. And as it does, it's going to reach some final position. And that final position is going to be defined by the fact that it's not moving there. If it's not moving, it's got no kinetic energy. But that energy that was in the motion was put back into the spring. So it has the potential for motion. Okay. And again, our initial energy is K naught plus U naught. This is 0. So it's 1/2 mv naught squared. Okay. Our final energy is K plus U. No motion at that point. 1/2 kx squared, and they're equal. So, 1/2 mv naught squared is equal to 1/2 kx squared. The halves cancel. If I solve for x, it's the square root of mv naught squared over k. The mass was 2.50 kilograms. The velocity was 1.72 meters per second. We got to square that. And then the spring constant again was 330 newtons per meter. And if you do this, you're going to get 0.15 meters. That sounds familiar. Oh yeah, it's this. Well, now that's interesting. So what this means is that if I were to release the spring from a position about the equilibrium position, it's going to bounce back and forth basically. See, in part B, if you were to sort of think about what the spring does beyond that, the spring is now compressed, so it wants to push the mass back to equilibrium. But it's been compressed by the same amount as it was in part A. And if you follow these energy arguments, when it crosses the equilibrium position, it's going to be traveling at 1.7 meters per second to the right. It travels past it because of this inertia. It stretches now 0.15 meters and then back to the left. So the spring is going to oscillate back and forth like this. Okay. Now, this type of behavior is called simple harmonic motion. And it's some of the most important behavior that you see in physics. All sorts of things exhibit simple harmonic motion. For example, if you think of the Earth going around the sun, it goes around the sun once every year. That's consistent periodic motion. That's simple harmonic motion. If you think of the conditions that we needed for uniform circular motion is simple harmonic motion. Spring motion back and forth, simple harmonic motion. The swing of a pendulum back and forth around an equilibrium position, simple harmonic motion. Okay, and what's important about things that exhibit simple harmonic motion is that things like springs are some of the only solvable problems consistently across physics. You can solve spring problems in mechanics, which is what we just did. You can solve spring problems in quantum mechanics. You can solve spring problems in relativity. So all of these areas of physics provide places in which the spring problem is something that can be solved. Now you might be asking yourself, okay, so what is a spring, right? Well, check this out. If you think of the inside of a material as being made up of atoms and molecules, we think of the bonds as springs. They're approximated using springs. Okay. Many types of incredibly complicated problems boil down to you just having to solve a spring. I say just, the devil's in the details. But that's what it is. It's an incredibly important problem. And it's very easy, as you can see, using energy. Now let's do a not so easy problem. Oh, actually, this is an incredibly easy problem. A cart on a roller coaster starts from rest on a track as shown. If A is equal to 50, so it starts at 50 meters, and B is equal to 33, this is 33 meters right here, how fast is the cart traveling at locations B and at location C? C is the ground. Now, you see how crazy this track looks? Quite honestly, what was that place somewhere in central United States that the guys were building roller coasters that weren't tested and they were like decapitating people? That's kind of like what this would look like. I think this cart's going to hit here and it's going to launch off, and then it's going to be like, all hands lost, basically. But in lieu of that, let's pretend that it's a fun ride. You see how complicated this track is? If we were to use the arguments that we've used up to this point and not energy to solve this, this would be a nightmare. Okay, this would be a nightmare. But check this out. So what are we given? We are starting at location A, which I'm going to call H sub A. It's 50 meters. H sub B, 33 meters. And H sub C is 0. That's how high above the ground we are. We also know that our velocity at A is 0. It starts from rest. What I'd like to find is the speed at B and the speed at C. Oh, how are we going to do this? Not giving enough information, right? Wrong. Watch. So let's talk about the energy at location A. At location A, your energy would be a combination of kinetic energy and potential energy. But look, it's starting from rest, which means that there is no energy in the motion. And the thing that's making this thing move is gravity. Gravity is the thing that's pulling this roller coaster down the track, which means that the force, in lieu of talking about friction, which we're not going to do yet, that we have to deal with is simply just gravity. Okay? Which means that this is mgh sub A. Now let's talk about location B. Well, at that point, based off of the problem, this cart would be moving to the right. It's going to have kinetic energy. Plus, it's going to have potential energy because there's still potential for motion towards the ground. What do those look like? 1/2 mv sub B plus mgh sub B. Now let's talk about the energy at location C. At this point, there's no more potential for motion. The cart's just going to track off to the right. So my energy at location C, which would be a combination of kinetic energy and potential energy, is just kinetic energy because it can't move past that point. 1/2 m v sub c squared. Now, this energy is equal to this energy is equal to this energy, and this energy is equal to this energy. They're all equal to each other because energy is conserved. As long as you add up all the energy, the number doesn't change overall. So, if I want to find, for example, how fast this cart is traveling at B, well, I should compare these two right here. This gives me my initial energy. This is how much energy I have overall. Whatever this number is going to be the same as whatever this number is. It's going to be the same as whatever this number is. So I want to compare EA to EB. When I do that, I have MGH sub A on the left-hand side. And on the right-hand side, I have 1/2 MVB squared. I'm not sure where that square went. Plus MGH sub A, right? Should be rather. Now, I want to find VB, but I'm going to do an intermediate step to sort of prove a point. I'm going to move this to the left-hand side and then flip sides, obviously. I'm going to pull the MGs together. This is the difference in height. So like I said, it's the difference between two positions in space that power this. Not the values independently, but the difference between them. Remember, from here, this right here is the difference. Okay? Excuse me. So, again, masses don't matter. Whoa, well, that's interesting. VB here is going to be the square root of 2 times G times HA minus HB. Again, it looks very familiar. 2 times 9.8 meters per second squared times 50 meters minus 33 meters. So if I were to do this, two times 9.8, oops, not 908, times, use my cell phone calculator. I can't believe that little toot took that, man. She's hilarious. Okay. So here it ends up being something like 18 meters per second. Okay. Or if you put it in sig figs, it would be about 20 meters per second. All right. Now, what I'd like to do is to find out how fast this thing is traveling at location C. Well, I'm just going to compare EA to EC. You could compare EB to EC if you'd like. It works just the same. It's just a little bit more work. Okay. Because, you have two things here instead of one thing here. And why make yourself do more work? So EA, once again, MGH sub A, EC from over here, 1/2 MVC squared. So the masses cancel again. So V sub C is the square root again of 2 times G times H sub A. So the square root of 2 times 9.8 meters per second squared times 50 meters. And if you do the math there, 2 times 9.8 times 50, I get 31 meters per second, or, keeping sig figs, 30 meters per second. So there you go. A problem that would be damn near intractably difficult to do, at your level of education with respect to physics, it would cause an undergraduate student to get nervous. Even if they were up for division, they would look at this and say, "Oh man, this is going to suck." But using energy, it's trivial. It's an incredibly easy problem to do. Now, so that said, you can combine energy. And so as an example, we have a jumping spider toy that has a small plastic base, and there's a spring attached to the plastic spider. When the spider is pressed down and the spring is compressed, a sucker attaches to the base, which releases suddenly and randomly. It's a random thing. Causes the entire toy to spring up into the air. If the spring has a spring constant of 300 newtons per meter and is compressed 2 centimeters when pressed down, how high into the air will the toy spring? Assume that the toy has a mass of 50 grams. Now, so these things kind of look like this, just to give you a sort of sense of what you're looking at here. You have a base like this. Usually it's got a little hard plastic, we'll call them dongles, that sticks up like that. So you have the circular base like that. And then there's a spring that looks a lot like, say, the spring inside a pen or something like that. And the spring winds up, this way. Okay. And that attaches to usually a sleeve of some sort. So you'd have a hollow thing that's just a little bit bigger than that dongle. And on there, there's a plunger. And by plunger, it's like one of those little suckers that, you can stick to things to glass with. So it's this sort of, circular sucker thing. And then, you got your spider here. I'm not very good at drawing spiders, so there's a spider, we'll say. So when you press this thing down, what it does is to compress the spring, and then the sucker attaches to this, like I said, kind of like a piece of glass. But because this thing is pushing up, what it does is to cause it to unseal, and this sudden jump up of inertia, causes the entire thing to spring up into the air. Okay, they're kind of fun to play with. Okay, so that's the general idea. So if I were to draw a picture, just sort of detailing, what's going on in the problem, we'll say, and this is the direction of up, like this. Whoops. Then, here's my toy right here. I'm just going to draw as a little circle. Okay, so I compress it, and it releases with an initial velocity. and then pops up this high up into the air. And we'll call this, since this is y-axis and this is x-axis, I'm going to call this h, this high above the ground. And we know at this point, from our experience in, chapter 3 and chapter 4, that the velocity at this point is going to be 0. Now, the act of compressing this thing compresses the spring. So you push it in, it compresses, and it sits at rest, which means that if I think about it, my initial energy, which would be a combination of whatever the kinetic energy this toy has and plus whatever the potential energy it has is, well, the toy isn't moving because it starts from rest. So really what's happened is I've compressed this thing, and it's a spring. So I've compressed it that far. Now, so it releases, this thing bounces up into the air, and then it stops up here. Up here where your energy would be a combination of kinetic energy and potential energy. But it's not moving because gravity has halted it. And, gravity halted it, which means that my potential energy up here must look like mgh. Wow. I'm getting a sense that this problem might be pretty easy. In fact, let me write out my givens. Okay. My spring constant, we know from our problem, is 300.0 newtons per meter. The mass of my toy here is 50 grams, which we'll write as 0.050 kilograms. And it's been compressed this far, 2 centimeters. Okay? And I'm trying to find H. It's that easy. This energy is equal to this energy. E is equal to E naught. So mgh is equal to 1/2 k x naught squared. And all I'm doing is solving for h. H is 1/2 k x naught squared divided by m times g. So 1/2 300.0 newtons per meter, 0.02 meters. You got to square that. Don't forget to square it. The mass, 0.050 kilograms. And then there's a g down there, 9.8 meters per second squared. So here, it's a half times 300 times 0.02 squared. And then I got to divide that by 0.05 rather, times 9.8. .122 meters. Okay, or keeping to sig figs, I see 2 here, 1 here. So this ends up being something like 0.1 meters or 10 centimeters. So it bounces up in the air 10 centimeters. You see how easy this was? Energy is an incredibly powerful tool. Now, the big thing you have to watch out for is that it's like a hammer. I imagine most people who are listening to this, watching this, have heard the analogy that if the only tool you have is a hammer, then everything looks like a nail. Well, we have more tools than a hammer. Okay, so energy might be incredibly easy and incredibly compelling because of that. But some situations it might be easier just due to the kinematics. Solve the problem. In some places you may not be able to use energy if it's not being conserved. We're going to be talking about that here in a moment. So let's do this problem now. You have a pendulum, and the length of the string in the pendulum is 75 centimeters. There's a mass on it. It's been displaced here with respect to a center line, which I'm going to call the y-axis, by 25 degrees. And the mass itself is 0.30 kilograms. And what I want to know is how fast is it traveling when it crosses this? Well, I mean, what's making it go? That would be gravity. So check this out. This is how high above the ground the pendulum is. And by the ground, I mean the release point. Or not the release point, rather, but where it ends up when it swings across the center line. So what you have here is, actually, let me do this. We'll dash it. Oh, I turn that off. Habit. So many of these videos. Oh, let me redo that. There. Okay, so this right here, this distance right here between the release point and where it swings down to the bottom. I mean, that's the difference in gravitational potential energy that's going to go into making this thing move, right? So what we need to know is how high above this point it is. Now I know where this point is in space. It's L. So if you think of the length of the pendulum as being L, then I know that from here to here, which would be the top to where this thing sort of swings through, I know that this distance right here, like I said, this is L. This is the length of the pendulum, which we've been given as 75 centimeters. Right? So what I need to find, though, is this position right here. I need to find that. Okay? So let's just put that on a separate line. So I need to find this distance right here. Oops. You know, this right here. So why don't we call this H? Okay, and we can actually find it here pretty easily because we have a trig problem here. This is a right triangle, right? This is the hypotenuse is L, and this side right here, which is the opposite side, would be a sine. So what I'm seeing here is that this is a sine, this is a cosine. Cosine would be this distance right here, right? So this distance right here, which I'm just going to call y for the moment, y is going to be L times cosine of theta. So this is y. So if I take L and I subtract away y from it, that gives me this. This is going to be h. And you can think of it like this. Y plus h is equal to L. H is equal to L minus y. All right. So here, if I take and I plug in, you know what y looks like, it's L minus L cosine theta, or L 1 minus cosine of theta. Okay, so this right here would be h, is this. And guess what? Oh, well, we're going to call this point the initial point. This is the final point. Will you agree with me that this thing can't be swung further to the right by gravity when it gets to this point? It's this inertia that carries it. Why, yes, that's true. So my initial energy, since this thing starts off from rest, okay, we want to find V. My initial energy here, which would be kinetic energy plus potential energy, well, there's no kinetic energy, it's not moving. My potential energy is mgh, and h is equal to L times 1 minus cosine of theta. At this point right here, my final energy would be K plus U. There's no potential energy at that point. 1/2 mv squared. And they're equal. The masses cancel. V is equal to the square root of 2GL 1 minus cosine of theta. Zero 0.75 meters times 1 minus cosine of 25 degrees. Sorry, I should have put that here. Two times 9.8 times 0.75 times 1 minus cosine of 25. Oops. Come on. All right. I get a 1.17. All right. Now if I stick the sig figs, I see 2 here, I see 2 here, I see 2 here. So something like 1.2 meters per second. But you see how easy that was? Right? So, like I said, the energy approach is incredibly, incredibly, incredibly powerful. Okay, so the next thing I'd like to talk about is what it means to be a conservative force. Because as I had mentioned earlier, not all forces are conservative. Basically, uh, you know, conservation of energy, we know, whoops, um, says that your initial energy and your final energy are the same. Basically, your energy at all points when you add it all up is constant. And we had extended this to basically just if you take and you move the initial over to the other side, that means that your change in energy overall is zero. But there are situations in which it's not equal to zero, and a good example of which would be when you have frictional forces that are present. If you have energy from outside the system, and by system I mean the problem that you're working, or whatever physical situation you're looking at. You could have energy coming, in from the outside, or actually leaving to the outside, which actually will be a topic that we discuss when we get to University of Physics 2 and thermodynamics. Now, that said, the way we think of a conservative force comes from mathematics, specifically, math's treatment of fields and things like that. And the idea is that you have a conservative field, and by field I mean a whole bunch of vectors, uh, basically a function that defines vectors. You have a conservative field when you integrate your field over a closed path, and you get zero. All right. So the little circle here means closed, a closed path. So, for example, let's pretend that we were looking at a particular force or something like that, and we wanted to see if it was conservative. This would be an example of a closed path. We could say that we start here. This is our initial position. We'll call it A, and we also end here, which will be our final position. So here's your closed path going this way, this way, this way, this way. And by closed, there are no gaps or breaks in our little loop or whatever it is here. So let me show you an example of a conservative force, one that we've actually already dealt with, and that's gravity. So I want you to imagine, we'll say that this is the floor right here. And so what we're going to do is we're going to take a crate, and our crate's got a mass, And what we're going to do is we're going to move our crate from here to here, from here to here, whoops, to here, from here to here, and then back to our original starting position here. Okay? So what I want to see is if I look at how gravity behaves, like how much work basically gravity would be doing here. What I'd like to do is to examine it along each of these paths. Now I'm going to break this up into 4. There's path 1, up, 4. There's path 2. There's path 3, and here's path 4. Now we'll start here at 0. This we'll say is I don't know. This is x and y right here. Equal to 0. And so I'm going to go from here. I'm going to go to a distance L. Get off the line mode. A distance L here. I'm going to lift it a distance up here. I'm going to move it a distance back L here, and then down, of course, L. So if you look at the force due to gravity, the force due to gravity in general looks like, at least in a situation like this where gravity is pointing down to the ground, minus mgy hat, right? Now we have 1, 2, 3, 4 different delta R's. So this right here, I'm going to call delta R1. It is L x hat, if we call this x and we call this y. This right here would be delta L2, or delta R2 rather, which would be L y hat. That's how far we go. This right here would be delta R3. We're going minus L along the x hat or direction. And then down this way, this would be delta R4, which would be minus L y hat, because we're going from here down in a negative direction. So here, what I want to do is to look at this closed path and I want to examine the force due to gravity, okay, along this closed path. And we're using dl here for path. This is the same thing as dr, okay? Now, so thankfully, since we have a constant force, this closed loop, this would be a work integral around a closed loop, really is just f dot delta r1 plus f dot delta r2 plus f dot delta r3 plus f dot delta r4. So that's the total path around our loop right here. Okay, now the f in each case obviously is the force due to gravity. And so the first thing I'd like to point out is here on part 1. This right here is the direction that we're moving the crate with our arms. And this right here is the direction that gravity is trying to work on the crate. And what you'll notice is that this is a right angle. And we know when we do dot products like this, no amount of gravity is assisting us in moving this thing side to side. So this is 0, the first one. Now we can make the same argument here for part 3 of our path. Okay, we're moving it this way with our arms, but gravity isn't assisting us at all because gravity is trying to pull us down to the ground. So in this situation right here, again, it's a right angle, except now instead of this being dr, this would be dr. So along the third path, that's 0. So the only ones that we really have here that contribute anything worthwhile would be this one right here and this one right here, the one for path 2 and the one for path 4. Now, so that said, excuse me, for path 2, this would be the direction. So this is for 2. This would be the direction of delta r, But this right here is the direction of our force. So if you look at this one right here, this would be, minus mg y hat dotted with L y hat. Now, when you do this dot product, you get minus mgl. For this one, though, we're moving it down and gravity is also pulling it down. So what that means is that if you were to do this one, it would be minus mg y hat dotted with minus ly hat. So when you do this one right here, you end up with plus mgl. And when you add these together, you get 0. Okay, so in this case, when you look at the work done by gravity around a closed path, you get 0. And this path here could be arbitrary. It doesn't, I mean, in this particular case, we just chose a square because the geometry of the squares are easy. But you could make it, as weird as you wanted, as long as you can parameterize that weird loop. You're going to get 0 when you do it. Okay, and so that is sort of the defining characteristic of a conservative force when it comes to energy. And that's if you look at the work done around a closed loop by that force, you get 0. Okay, so that's how you can tell if a force is conservative or not. Now, as a counterpoint, let's think about a different force. So I want you to imagine us looking down on a table. So here's a tabletop, for example. And what I'm going to do is we're looking overhead down on it. And here's a block. It has a mass of m. So here's its mass right here, m. And what I'm going to do is to move this thing from here to here, from here to here, from here to here, and back to here again. So we're moving it from here to here to here to here. Now we're going to assume, again, that we're dealing with a square and all sides have a length of L. But I want to be very clear. We're looking down onto it. So gravity is trying to pull it down through the tabletop into the screen or into the sheet of paper, if you want to think of it like that. So what I'd like to do, like I said, is to take a look at friction. Now, when I move this thing this way, so this would be, for example, we'll again number them 1, 2, 3, and 4. Okay, when I move this thing this way, friction is resisting that, and as a consequence, is giving you a force in the opposite direction. So, for example, for part 1, whereas this might be the direction of delta r, and for part 2, this would be delta r, and this would be delta r for 3, and this would be the direction of delta r for 4. And let's just go ahead and write those out if we sort of give us a coordinate system here. And I'll use y and x, except obviously this is going to be along a flat surface like this. So let's draw it like this. So here's y, here's x. So for part 1, delta r1 would be L along, the x hat direction. Delta r2 going up this way would be, L along the y hat direction. Delta r3, is going to be, in the minus x hat direction, and delta r4 is going to be down the minus y hat direction. But here's the thing, though. If you look at the force, right? So for part 1, the force is going to be this way. For part 2, the force is going to be this way. For part 3, the force is going to be this way. And for part 4, the force is going to be this way. So you have, these 4 cases with these frictional forces in which they're always opposing, the direction that we're trying to move this thing. Okay, so if you look at the work done just by the frictional force, there are no situations here in which you get positive work because friction always acts to slow things down, which means that the work for this one, if we call our frictional force F sub k, and we just assume that it's constant, which it will be, given normal forces and things like that. So for part 1 here, this would be, minus F sub k x hat. For this one right here, this would be minus F sub k y hat. For this one right here, this would be f sub k x hat because it's going to the left, or to the right rather. And for this one right here, it's going to be back up this way, which would be f sub k y hat. If you look, for example, at the work here for 1, it's going to be, f sub k for part 1 dotted with delta R1. But here's the thing, right? F sub k is minus f sub k x hat. When you do the dot product here, you're going in L x hat direction. So this is minus, f sub k. That looks ugly. F sub k L. If you do the work for the second one, okay, the second one is going to be minus f sub k y hat dotted with L y hat. When you do that, you get that. When you do this one, you're going to get the same thing. When you do the last one, you try it, get the same thing. And when you add these, all of these up to look at, excuse me, to look at the frictional force, when you look at the line integral here around this closed loop, you do not get 0. Okay, so this right here, this is a non-conservative force. Now, obviously, we love conservative forces because conservative forces mean that we can exploit conservation of energy and we can do problems like this. The spring force, for example, is a conservative force, right? So in a situation where you have a non-conservative force, you can make energy arguments, but you have to be very careful about it. And we're going to do examples of that in the next video, okay? But a case in which you have a conservative force, this situation right here, we're in a good state when that happens. Now, when you have a conservative force, that also means a few things about the force itself, okay? So if you think about this integral right here, okay, it turns out one of the implications, and I'm not going to get into the mathematics of it, if you are genuinely interested in it, it could be in Calc 3 that you talk about Stokes' theorem, and that you talk about Gauss's law. Okay, so these are two mathematical laws that you see used extensively in physics as well. We'll be seeing these quite a bit in university physics too. That said, one of the consequences of this right here means that you can write your force in terms of your potential energy. Okay, for example, we know differential work is defined this way, right? So I would like to just consider this along one dimension for a moment, and also point out that this is the same thing as minus du. Okay, so it's also the same thing as dk. If you think about taking your deltas and promoting them to differentials, which we do all the time. Okay, so that means the same thing. You can prove it to yourself if you want. For example, if you integrate du from u naught to u, you're going to get u minus u naught, which is delta u. You put a minus sign in front of it, and guess what you get? So anyway, let's just look at this along one dimension. So imagine some weird conservative force that operates along one dimension, like maybe gravity, for example, just up and down the y-axis. So in that situation, we'll stick with x just for the moment. Your dot product over here looks something like this. F sub x will say dx. Whoops, just the x part, right? And on the right-hand side, that looks like minus du. So if you move the dx to the right-hand side, f sub x would equal to minus du dx. Okay, you can imagine extending this to more than one dimension. F sub y would probably look like minus du dy, and f sub z is going to look like minus du dz. Now, the reason why this is the case and why we know that u would change with respect to x, y, and z is that in general, for a conservative force, it is a function of position only, okay, if it's conservative. Okay, you write it as a function of position only. Now, so the issue that we have here is that if it's position, you might be depend upon x, it might depend upon y, and it might depend upon z. Now, so depending upon how far you've gone in the calculus sequence, that's problematic for a derivative that looks like this. This is a standard regular derivative. Okay, so for example, if you were to take the derivative of this with respect to x, you would want to know, how y changed with x and how z changed with respect to x. Okay, to carry that derivative out. Or you can do something called a partial derivative. Okay, so basically what you do is you take the d's and you promote them to these weird script d's that look like that. And when you take the derivative of, we'll say u with respect to x, what you're doing is you're holding y and z fixed when you do it. Okay, so we can write this as well if you think of extending your force to a vector as minus du dx x hat minus du dy y hat minus du dz z hat. Now, du, whoops, get rid of that. It's actually misspoke. Z hat. D by dz, from a partial standpoint, z hat. D by dy, y hat. D by dx, x hat. This has this operator we call, say, derivative, has a special name called the gradient. It's an upside down triangle with a little hat over the top. And it turns out that conservative forces you can write as minus the gradient of the potential energy. Okay. Now, we will be using this a little bit, specifically in University of Physics 1, or not 1 rather, but 2. But I don't want you to worry so much about that. I just wanted to point out that in the event that you have a conservative force, this is the relationship between the force and the potential energy. Okay. So we could test it real quick if you'd like. If we go up here and we go way back up here, and we take a look, for example, when we're looking at conservation of energy and these sorts of things, and we look at the potential energy, for example, of a spring right here. So along one dimension, our force would look like minus d by dx of our potential energy. You take that derivative, you get minus k times x. And there's your spring force. Okay, so as you can see, that can be incredibly convenient. And it's actually something that's extensively used as you do more advanced physics. Now, so this is the long and the short of conservative forces, what it means to be conservative, what it means to be not conservative, and also, how you use conservation of energy and what potential energy is all about. Now, next lecture, we're going to have a discussion about, some of the non-conservative approaches that we can take to dealing with energy. And also, we're going to talk about what happens when you plot energy, because it turns out plotting energy and looking at overall energy and the behavior between kinetic and potential can actually tell you quite a bit of stuff about your problem. And I will see you then.